So in earlier videos, I have alluded a couple of times that we would get to a different way of counting atoms and accounting for how many atoms were in each type of molecule. And we're finally going to do that. And what I'm talking about is this concept of moles. So moles is a way of counting atoms by weighing them. It is also referred to as the chemist's version of a dozen. And this is because it is a word that we use all of the time without ever explicitly stating the number, although what we're going to do is use that as a conversion factor and in a bunch of calculations. But if someone says a dozen, you automatically know in your head, you formed this association that means 12. Or if someone says a pair, you know that means 2. And there are a lot of words that, especially if you use them regularly, you recognize that the word that doesn't have a number in it means a specific number. So for a chemist, this is a mole. And there is a video on Canvas that you can take a look at if you want a little more background and just to watch what's a pretty good video that's also a cartoon, so that never hurts. So 1 mole is actually a huge number, and I'm going to make sure that I have some explicit pieces in here. I'm going to say 1 mole of particles, and it can be any kind of particle, and I'll show you once we get the number down, is equal to 6.022 times 10 to the 23rd particles. So an absolutely huge number, and also this is Avogadro's number. And when you see it abbreviated, you'll also see it as a capital N with a lowercase a. And so if you see that, it means the 6.022 times 10 to the 23rd. All right, so 1 mole of particles. So this means that if you have 1 mole of marbles, this is equal to 6.022 times 10 to the 23rd marbles. It's a lot of marbles. If you have 1 mole of carbon atoms, that's 6.022 times 10 to the 23rd carbon atoms. If you have 1 mole of CO2 molecules, that's 6.022 times 10 to the 23rd molecules. And so, okay, so we've got the counting part. The question is, where does the mass come in? So the mass comes in because 1 mole of carbon atoms, for example, if you have a sample that has the same percent natural abundances that you would find in, just like the representative sample that we talked about when we talked about isotopes, it would weigh 12.011 grams. So also, if you weigh out 12.011 grams of carbon atoms, you have exactly 1 mole of carbon atoms. And hopefully you recognize this 12.011. This is the atomic weight from the periodic table, except we put it in grams instead of AMU. So this is what we call the molar mass. So we've got moles, which are Avogadro's number worth of particles. And when we connect that to the actual mass, we call it the molar mass. which you will see abbreviated with just 2 capital M's. Sometimes in textbooks you'll see it as just a big uppercase fancy M, but it still means molar mass. And this is the mass of 1 mole of atoms of an element. And in grams per mole, this is numerically equal to the element's atomic mass in AMU. Okay, so this also applies to molecules, and because it also applies to molecules, depending on the resource that you look at, sometimes you will see this listed as molecular weight and abbreviated MW. These are used interchangeably. The thing is, as long as we're on Earth, it doesn't matter because mass and weight are different technically, because weight depends on the gravitational pull of where you are. And since we're doing all of our chemistry on Earth, at least for the moment, as far as I know, we can use these for the same concept when we're talking about them. So I will use molar mass. You may see molecular weight written places, but it means the same thing for our purposes. So if you kind of expand this up to looking at an entire molecule, let's look at carbon dioxide as an example. If we had just one molecule, well, there's 1 carbon in here, which that carbon atom weighs 12.011 AMU, and there are 2 oxygens that weigh 15.999 AMU. And so 1 molecule weighs 44.01 AMU, and this will be referred to as the formula mass. Now, we're not going to use it really with AMU on here. What we're going to think about is scaling this up to an entire mole of carbon dioxide molecules. And so the molar mass of carbon dioxide is 44.01 grams per mole. And we'll be able to use this as a unit conversion, and we're going to have some practice with that. So what I'm going to do is pause the video, write out a couple practice problems, and then we'll come back and take a look. Our first example is to calculate the molar mass of C6H12O6. So we need to add up the atomic weights for each of the elements that we have here based on the number that are in the molecule. So just to get everything organized, you don't have to always lay it out this way, but I think for getting started, it's a good way for us to keep track of things. My carbon from the periodic table, I can pull the 12.011, and there are 6 of them, so I'm going to need that times 6. The hydrogen is 1.008 for its atomic weight, and I have 12 of those. Oxygen is 15.999, and I have 6 of those. So my carbons are 72.066, hydrogen 12.096, oxygen 95.994, and if I add all of these up, it is equal to 180.16, and my units are grams per mole. For example 2, it says, how much sodium oxide should you weigh to obtain 4.02 times 10 to the minus 2 moles of sodium oxide? And then how many molecules is this? So for the first question, I know how many moles I need, and it's asking me to figure out how many grams this is. So what we're doing here is we're using the molar mass as a conversion factor. So my units are grams per mole for the molar mass. So if I just look back at my C6H12O6, 1 mole is 180.16 grams. So I can write that in the format of a conversion factor. Now, I'm dealing with sodium oxide this time. I need to actually calculate the molar mass of that before I can use it. So let's set that up. I'm going to set it up in a different format. This is a little bit faster to write out. It's definitely a lot faster to plug into your calculator. So the sodium, I had 2 of them, and each sodium weighs 22.99 grams per mole. And I've got 1 oxygen, obviously you don't have to write the 1 there, times 15.999 grams per mole. And when I add this up, I get 61.979 grams per mole for my entire molecule. So I know that I need 4.02 times 10 to the minus 2 moles of sodium oxide. And I just calculated the molar mass. I know that 1 mole of sodium oxide weighs 61.979 grams. And the way that it's set up, moles of sodium oxide cancels with moles of sodium oxide, and I will end up with grams of sodium oxide. So if I just multiply this through, that's 2.492 grams sodium oxide. So if I were in the lab, say using this chemical, and I've figured out from my reaction, which is something that we work on in Module 4, exactly how many moles of sodium oxide I need. Now, because I also know the molar mass, I can go over to the balance and weigh out this amount, and I'll have pretty close, because you won't be able to get this perfectly, pretty close to the right amount for the reaction I need to do. Okay, so the second question was, how many molecules is this? So the only conversion or relationship that I have to molecules is Avogadro's number, and that relates to moles. So I'm going to start with the same information that I did for the first question. I don't have to use the grams value because Avogadro's number lets me go from moles to molecules. So I want to start again with 4.02 times 10 to the minus 2 moles of sodium oxide. And I know that 1 mole of sodium oxide contains 6.022 times 10 to the 23rd molecules. And so this would be 2.42 times 10 to the 22nd molecules of sodium oxide. So you can see why we like weighing things out on a balance as opposed to trying to count molecules, which are really tiny, would take us a long time. It's much more practical to weigh things out on a balance, and this is a fantastic relationship that you will use in every single chemistry class ever, and probably in a lot of non-chemistry classes as well. Okay, So I want to do one more thing in this video, and I want to take what we built up with formula mass, molar mass, and look a little bit more closely at some of the molecules. So I want to use the C6H12O6 as an example. And if I pull out part of what we did for calculating the molar mass, we did 6 times the molar mass of carbon. And from this, and I did that because I had 6 atoms of carbon, six atoms of carbon in one molecule. Well, when I scale that up to think about this in terms of moles, if I had 1 mole of C6H12O6, this molecule, we'll say, actually, 1 mole of this molecule has 6 moles of carbon atoms in it. We're going to use this in just a couple minutes in an example. So 6 moles of carbon in 1 mole of this molecule. So that is true for every element that is in this molecule. So there are 12 moles of hydrogen atoms and 6 moles of oxygen atoms. All again in 1 mole of the entire molecule. All right, so an example of how you might see this, we'll say, how many moles of carbon could be extracted from 1 kilogram, say 1.00 kilograms of C6H12O6. So this has a bunch of pieces here. So I need to somehow get from kilograms of C6H12O6 to moles of carbon. Well, I definitely have to get to moles of C6H12O6. And then I should be able to use this relationship about how many moles of carbon are in there based on the formula of the molecule. What I'm starting with is 1.00 kilograms. So I do know the molar mass of the C6H12O6 because we calculated it in an earlier example, but that relationship is in grams, not kilograms. So I should first get this. I know that 1 kilogram is 1,000 grams. So when those cancel, I'll be in grams. And then I know that this molecule, there are 180.16 grams in 1 mole. And the latest thing that we've added, I know that in 1 mole of this molecule, there are 6 moles of carbon atoms. So this conversion factor, this relationship here, is the most recent one that we've added. And so if I plug all of this into my calculator, I get 33.3 moles of carbon.